Alrighty, guys, can you hear me? Awesome. Are there any questions or comments before we get started? Right. So today is going to be the last lecture we'll do on chapter 2. So let me switch over to the document camera. Right, so next week we're going to start on topology. This is we're going to start on topology, and this is chapter 3. Right, so today we finish. We're going to wrap up series and sequences. And the big buzzword today is today's buzzword is Cauchy. So today's buzzword, this is going to be Cauchy. So that's going to be the big new thing in today's lecture. And the way that I'm going to get started on these Cauchy sequences is by looking at an example. So we're going to be looking at an example. So this is an exercise. This is exercise 245. And what this here is, it's an example of this is a sequence in Q with a limit in R, but not in Q. Okay, and this limit here, this limiting point is going to be the square root of 2, which is we saw in one of the very first lectures, right? This is an element in R, but it's not in Q. This is going to be linked to these Cauchy sequences that we're going to be talking about after this example here. And so the example, this exercise here, he constructs, there's a recursive construction of this sequence, of this xn. So the way he does it, so you want to create something recursively, you start out with the first point, right? So that's going to be x1. And the first point that he starts out with is 2. And then the next point, well, the next point is going to be generic. This is like xn plus 1. It's going to be 1/2. And then it's xn plus 2 over xn. Right, so if you look at some examples, like say x1 is 2. So this formula here, if you were to get like x2 would be 1/2 times x1 plus 2 divided by x1, right? So that would be 1/2, and then it would be 2 plus, well, I guess 1. So this would be 3 divided by 2. Right, so this here is, of course, a rational number. Right? That's in Q. This is a rational number. This is in Q, and so on. So if you took x3, you write that as 1/2 x2 plus 2 divided by x2. And we'll plug in, we'll get a half times 3 over 2 plus 2 divided by 3 over 2. So this will come out to be something like a half 3 over 2 plus 4, what would it be? Can I figure this out? If I divide by 3 over 2, this is 4 divided by 3, something like that. It's going to be, again, a rational number. This is how we construct a sequence. We have a starting point, and then the next point is given according to this formula. And so the exercise, I'm going to show you the exercise. Show you the exercise. The exercise says compute this limit here. So we have to establish that there is a limit, and then you have to compute what the limit is, right? And it says calculating square roots, right? So the limiting object is going to be square root of 2. Right, so what we have to do is we have to prove our goal is to show that the limit exists and that the limit as n goes to infinity of these xn's is going to be exactly square root of 2. Like equivalently, we can square both sides. This is equivalent to showing that the limit of xn squared is going to be 2. Like these x's are all positive. And so how we're going to go about doing that? So the first step is prove that xn squared. So this is like step 1. Prove that this thing is bigger than 2. That's the first step that he's asking us to do. Prove that this is bigger than or equal to 2. Okay, so we're going to do this. We're going to use induction, like what you did in the homework. We're going to use induction. So for when I look at n equal to 1, okay, n equal to 1 to have a 2 here. So we'll square 2 wholes. This is okay. And then you're going to make the assumption, assume that it's okay for 2, 3, all the way up to n. And then you're going to prove for n plus 1. So I need to prove that xn plus 1 squared is bigger than 2, but I have a formula for it. So if I plug into the formula, I have a square, so I'm going to put the square outside. So I put the square outside, and I take the formula, and I stick it into the parentheses. I get 1 over 2 xn plus 2 divided by xn, and I have the square. And so let's work out. So I need to show this thing. Right, this here is my definition of xn plus 1 in terms of xn, and let me work out what the left-hand side is. The left-hand side is, well, I get a quarter outside, then I have an xn squared, then I have this thing squared, so this is 4 divided by xn squared, and then I'll have 2 times the product, so that'll be 4 times xn divided by xn, so they will cancel. So lots of things here will cancel. This thing will cancel that one. And then I have a 4 out here. What am I left with? I'm left with 1 over 4 xn squared plus, then it'll be 1 over xn squared plus 1. Right, so I need to prove that this thing here is bigger than 2. So how would one go about doing that? Well, the thing that we know that xn squared is bigger than 2. So how small can this guy there get? Well, we could plot it, use Mathematica. Maybe I can show you how to do that. So that's one. If I were to study this thing and prove that it's bigger than 2, when xn squared is bigger than 2, one thing we could do is we could plot it. So maybe I can just start by doing that. So let me share a Mathematica screen. Right, so I could start by plotting just to get an idea about whether or not this is true. Right, so I'd have a divided by 4 plus not divided by a divided by 4 plus 1 divided by a plus 1. Right, I want to look at this thing for when a is bigger than 2. So let's look at the picture. And we get something like this. And it sure looks like this function here is it's going to be increasing. So, and the value that it has when it's when a is equal to 2 is exactly 2. So the only thing I really need to prove, is, for example, that it has a derivative which is increasing, or which is positive, so the function is increasing. So that'll be one way to do it. We could also just try to minimize it and see what you get when you minimize. But if I minimize this function here, I could even try to minimize it perhaps a little bit to the left as well. So if I go to 1 to 10, you can see that it has a minimum at 2. Okay, so could I prove stuff like that? Well, yeah, we can do that. We can look at, we can try to minimize. We try to minimize 1 over 4 times a plus 1 over a plus 1. Like, and I really just want to minimize this over a's that are bigger than 2. And so what we will do is we'll take a derivative with respect to a of this thing and put it equal to 0. And if we do that, okay, so take the derivative, we get a quarter plus, and then it'll be minus 1 over a squared. I want this to be equal to 0. And then we solve. Right? This is the same thing as saying that a quarter is equal to 1 over a squared. And then we're going to get that a squared is 4. We're going to get that a is 2. Right, so this minimum that we saw on the picture is really correct. It is minimized there. And the minimum value that you have was exactly 2. Right, so then we led to the conclusion that this is correct, because the minimum here is attained when xn squared is equal to 2. And then when you plug that in, you're going to get 2 here. This thing here is really bigger than or equal to 2. So this is okay. So we've proven that xn squared is bigger than or equal to 2. We did that simply by minimizing the quantity in question and prove that this minimum, when I plug in the minimizer xn squared equal to 2, I'm going to get exactly the value 2. So therefore, for any other value, it's going to be bigger than or equal to. So that was one thing that the exercise asked us to do. The next thing that the exercise asked us to do is to prove that you have a monotonicity property. Right? As soon as you see something that is monotone, then computing limits becomes much better, much easier, because we have this result that says that monotone limits, monotone sequences have limits. So let's try to do that one. So this is step 2. We want to show that that xn decreases. So show that xn is bigger than or equal to xn plus 1. So right, so it decreases. Okay, but the way that we do that is we again use the formula. We again use the formula that xn plus 1 is given recursively as a function of xn. So this is 1/2 xn plus 2 divided by xn. So we have to prove that this here is true. How would one go about proving that? Well, if I would subtract 1/2 on both sides, I'll get 1/2 on the left-hand side. So I'm asking, is this true? Is this true? Is this bigger than, well, what will be? It'll be 1 over xn. If the 2's cancel out, I get 1 over xn. So is that true? Well, let's have a look. If I multiply through with 2, I'm going to get that this is the same thing as saying that xn, I'll move that over, so I get a square. I'll move 2 over there, so I'll get a 2. And this, but this is true. This is okay by the first step. I shall have monotonicity. As soon as I have monotonicity, I know that I converge. So monotone sequences here, the decreasing. So monotone sequences, we have limits. We prove that at some point, as soon as you have monotonicity, you're going to have a limit, right? So this limit here, as n goes to infinity of xn, it exists. And so the last thing that the question is asking us to do is, so we've proven now that it's bigger than 2 and that it has this monotonicity property, and then we asked to conclude what the limit must be. Okay, so that's step number 3. And given that this limit here exists, the way to go about doing that is just looking at the recursion. What the recursion says is that you have xn plus 1 is equal to 1/2 xn plus, what was it, 2 over xn. So now we know that xn converges. So we just take limits. And I should call this limit here something, let me call it L. We know that this thing exists in R, right? It's going to be bigger than or equal to, when I square it, it's going to be bigger than or equal to 2. We'll take limits, right? So we get the limit here on the left-hand side is equal to 1/2, and then we have the limit on the right-hand side. This will be L plus 2 divided by L. Now, what is L equal to? So we have to be able to solve this equation. Well, we just have to identify what L is. So we can square. We square, we get 2 is equal to 1/4. And then L plus 2 divided by L squared. We factor out L squared plus 4 divided by L squared plus, and then the double product. This would be 4L divided by L. We had that one before, right? The L's cancel out here. So what kind of a solution are we looking for here? Well, let's try out. Our guess is that we want to try out that L squared is equal to 2. So then the question is, do we have the 2 is the same as 1/4 plus, and then what is it here? This is a 2 plus 4 divided by 2 plus 1. Does it look promising? Well, this one here is, it's not looking very promising. I made a mistake somewhere. This should be 4, it's not 4. I'm missing something. That's right. 4 should be a 1. 4 should be 1. Yeah, thank you. Does that look better? Gosh, I'm messing this up here. The last one should be. See if I can factor this out. So L squared, and then we're going to get 2 squared. This is a 4 divided by L squared plus, that is 2 times last one should be a 4. The last one should be a 4. And this should be a 4 divided by 2. Does that look better? Yeah, I think this looks better. Sorry. So this is 2 plus 2 plus 4. This is 8 divided by 4. So this is okay. Right. So there you go. So that was the last step. We identified the limit, but we cannot just, one could be tempted to just do step 3 immediately, but this is not good, right? Because we don't know that there is such a limiting object. We know from step 1 and step 2 that there is such a limit, so therefore we're able to take it. So this here is okay by step 1 and 2. There you go. Okay, so this here is an example, it's an important example on how if we were to just look for limit points inside inside Q instead of inside R, well, we wouldn't have this result that says that bounded sequences necessarily converge into something in Q. They do converge. We have proven that it converges into something in R, but not necessarily inside Q. And here was a specific example, and we're going to be using that example. We're going to be using that example next year when we start talking about Cauchy sequences. Any questions on the problem that we solved here from the textbook? All right, so where we at right now is we are working here in 2.6. So we're talking about this Cauchy. All right, so we're going to be talking about Cauchy sequences now and their properties. So definition: a sequence. So let's say AN is called a Cauchy. And here comes the definition, and it's quite similar in many ways to a limit, but it's not the same. It's a Cauchy sequence if for any epsilon bigger than 0, I can find a big natural number. And so far it looks a lot like the limiting point definition, but there's going to be an important difference here, such that for any n, and here comes a new thing, there's also an m. For any n and m bigger than this natural number n, what we have is that the distance between xn and xm, this is less than epsilon. Then you have a Cauchy sequence. And the big result, which you're going to prove today, this is the big theorem. This is that all so AN converges in R if and only if AN is a Cauchy sequence. So that's the big that's today's big big theorem that we're going to be trying to prove. But before we do that, I want to build up some sort of, I want to build up a bit of intuition about, like, what does it mean to be Cauchy? And for example, like you have N and M here, like, and there's no mentioning of any L here. Like here it says that AN converges, then we have to have a guess for what the limiting point is, and then we subtract that away here, and then you want to be less than epsilon in absolute value when you're sufficiently far out in the tail. There's no mentioning of that here, right? So there's no, it doesn't say L anywhere. So let's try to build up some intuition for this. So one could try this example that we've had. We studied it multiple times. So if I took AN and let it be this series where I go from, say, 1 to N of 1 over K. That's something we've had a number of times. And what we know is that AN goes to plus infinity as N goes to infinity. And we know that the series here, even though it decays, it really, when you add it up and you look at the limiting point, you're going to get plus infinity. There was an example we spent some time on a few weeks ago. So if one could ask for maybe we could just take M to be N plus 1 is good enough. I mean, of course it's not, because if that was good enough, the definition would have read that. Okay, so why is it not good enough? Well, let's look at this example here. So if I would look at a n plus 1 minus a n. So the thing that would be up here would be the sum from 1 to n plus 1 of these 1 over k's minus, and then the same thing, but just one less element in the sum. Like I'll just be left here. I'll just be left here with 1 over n plus 1. And this, of course, goes to 0. Like this goes to 0. So I'm going to have this property up here, but the series still converges to plus infinity. Right, so then if you were to replace m here simply by n plus 1, this theorem here could not be true. So this would, if this was indeed good enough, you would be in violation of the theorem. So it's not enough just to have m to be n plus 1. So what is enough to have? Well, you could try another example. What about if instead you wouldn't just have that the difference is small, but what about if it was really small? What about if instead that an plus 1 minus an in absolute value would be bounded by something that was much smaller? Like 1 over n is small and n is big, but it's not terribly small. So here's something that is terribly small. What about if I put 1 over 2 to the nth? Well, then I could look at, and the definition would require me to look at am minus an. And so I could write this out. This is this trick that we used a bunch of times. I will put in points like maybe I could put here instead of say something like an minus, and then say an plus m. Right, so I'm just instead of having m here, I'm just looking at m as being after n. What about if I would do something like this? Then I would be able to splash it out like n plus m minus a n plus m minus 1. And then I'll add it back on, a n plus m minus 1. And I'll keep doing this all the way down to the last one where I would have a, and then it would be n plus 1 minus an. So I could just add and subtract all the way between n and n plus m. And then I'll use the triangle inequality. This here would be bounded by, well, how big is this difference? How big are these differences? Well, now it would be, the triangle inequality would be a n plus m. Minus a n plus 1 minus 1 plus a. So we'll just put a bunch of them at dots. And then I would have the last one. This would be a n plus 1 minus a n. And now how big would these things be? Well, this here would be, each one of them would have this property. Right? So this here would be less than 1 divided by 2 to the n m plus, and then all the way down to the last one, this would be 1 over 2 to the n. So can I make this small? Well, I could factor out 1 over 2 to the n. Right, and then what I could have inside here would be like a 1 plus a half plus, at some point I'm going to get over 2 to the m, and I could just add more terms here. Again, then this big quantity here, this would be summable. And let's just double check that this indeed is summable. I'll just show you quickly how to do that in Mathematica. So what I'm claiming here is that if I'm summing 1 over 2 to the nth, and I'm summing n from, say, what does it go from 0 to infinity, I get 2. You get 1 if you sum here from 1 to infinity, and otherwise you're going to get 2. So this thing goes to 0 very quickly, and this thing here would be bounded by 2. Right, so when I choose n here, so for n sufficiently big, this thing here would be bounded by 2 to the n times 2. And then I can squeeze this thing here to be less than epsilon. I can squeeze this thing here to be less than epsilon by choosing n big enough. So for given epsilon, we can find a big N. Such that this difference, an minus an plus 1, this is going to be less than epsilon. Simply by choosing n here sufficiently big, I can squeeze this number here down to whatever I want. And what this example here shows is that it is possible to just look at the next element out, but it will require that you have a much faster decay to 0 than just decaying to 0 like 1 over n. That's not fast enough. If you want to have this property, you got to decay much faster. And for example, 1 over 2 to the n, this is going to do it. Are there questions on the examples we had here? Why did I choose? Because I knew that this thing here was going to go, this was going to work. This one here is one of the ones that decay fast enough, right? This decays much faster. This decays much faster than 1 over n, right? If you look at plots of these two things, you will see a big difference. Let me show you. Let me show you how that looks like in a picture, right? If I were to plot, I had 1 over n, right? And then the other one was 1 over 2 to the nth. Right, so if I plot these two next to each other and say n goes from 1 to 10, and one goes to 0 much faster than the other. The blue curve here goes to 0, right? We can put 100 up here. But you can see while the blue curve goes to 0, it doesn't go very fast. And this, the brown or yellow curve that we see, it goes much faster. And so that's why I chose it. You need something that goes super duper fast. You could try to experiment with other things too. You could try to have e, something like e to the minus n. That's also going to decay very fast. And you can see the green line, maybe 100 is too much, but you can see that the green line, the exponential function, it decays even faster, right? So I could also have chosen x of minus n. This is just an example. Why do I need to have it decay really fast? Well, because as you see, if it doesn't decay that fast, like if I am in this example, it doesn't work. If it doesn't, I mean, this series here diverges, right? It goes to plus infinity. And it's not a Cauchy sequence, because if it were a Cauchy sequence, it would have to converge. So this, it's true that these differences here, they decay to 0, but they don't decay fast enough to make the series convergent. Whereas if I speed up this convergence, if I speed it up from 1 over n to something like this, 1 over 2 to the nth, that is much faster. Well, this is fast enough to make the series a Cauchy sequence, and therefore it converges. Like that series that corresponds to the sequence here, it converges. It's not, this example here is the reason we spend so much time on this example is that this series here, it blows off to plus infinity, despite the fact that each element in the sum goes to 0. So it's not enough just to go to 0. You have to go to 0 quickly. Right? And so how quickly do we need to go to 0? Well, this here is sufficient, but of course not necessary. Yeah, there are other questions? Like, so for the series to converge, that sequence that you're taking the series of, that sequence has to vanish quickly. Otherwise, the series is not gonna converge. Are there any other questions, comments? Right, so the next bit of time you're going to be spending proving this theorem that says that all Cauchy sequences. We're going to be spending our time now trying to prove this theorem that we had here, that they converge. And of course, the reason that we're studying Cauchy sequences at this point is because we need stuff that we have talked about already. And so the big gun that we need is this Bolzano-Weierstrass theorem. So the first, there are lots of ingredients in this proof here, and so the first little lemma is that Cauchy sequences are bounded. Cauchy sequences are bounded, just like convergent sequences are bounded. Right? So how would one prove that? Well, the way that you go about doing it is if you pick epsilon to be 0 to be 1, for example, then you know that xn minus xm, this is bounded by 1. And this is true for any n bigger, n and m bigger than n. So this gives you control over the tail. And so what we've seen before is that we've seen this from here, the proof is exactly the same as saying when a bounded sequence is, when from here on, it's the same as the proof that convergent sequences are bounded. And then, so now we can just redo the proof we did, showing that convergent sequences are bounded. So flip through your notes and you'll find it in there. And the thing that's going to make it work now is that as soon as you have this boundedness property, then you're in business to apply the Bolzano-Weierstrass theorem, right? So proof of theorem, this is the one that says that Cauchy sequences are convergent. Right, so Cauchy sequences are convergent. Proof of this, well, you use because of boundedness, you can use the Bolzano-Weierstrass. And what the that was the one we proved last Wednesday, right? So it says that you can find a subsequence. So there exists a subsequence xnk inside xn, which is convergent. So there exists a subsequence which converges. So the limit as k goes to infinity of x and k, you're going to get a finite limit. Right, so the Bolzano-Weierstrass theorem, this is the one we had on Wednesday, where we said we're going to do this by section. So we're going to find, we have a bounded sequence, and here we do have a bounded sequence because we just argued. So if you have a bounded sequence, you can split this interval that is bounded in, and you can keep bisecting it into intervals that are half the size of the original one, and keep infinitely many elements from that set in there. And ultimately, you'll be able to extract a convergent subsequence. That doesn't say anything about, like the Bolzano-Weierstrass theorem doesn't say anything about the original sequence. It just says that you can find a convergent subsequence. And so what we're claiming here is that not only is the does there exist a subsequence that converges, it's the original sequence that will do it too. Right, so here's the claim. The claim is that xn also converges to L. Right, so we know that the subsequence does it, but now we're claiming that x itself also converges to L. And so how would one go about arguing that? Well, it is really just the definition of what it means to be Cauchy that will make all this work. So we call the definition of being Cauchy, it means that there is, no matter what epsilon you get, you can find an n such that for any m and n bigger than n, you have that the distance between xn and xm, this is going to be less than, say, epsilon over 2. Right? It could be for any epsilon, so in particular, I could pick epsilon over 2. So when I'm bigger than n, this is going to happen. And what does it mean? So this is the Cauchy property. Of xn. And the other one says that I can find, so this, the subsequence convergence, and there exists an nk bigger than n, such that, well, I'll have that xnk minus the limit. Well, this is going to be less than epsilon over 2. This is a convergence of x and k. This is a capital K, this is a little k. The convergence of this to L. But it means that this n here, when I'm past that n, the 2 points are close to each other, and inside the subsequence, these things are close to each other. And now it's just a question of using the triangle inequality. So by the triangle inequality, we can merge them. But I'm interested in how xn compares to xl. So I have xn minus L. And I'll do the usual trick, add and subtract the same thing. This is the same thing as xn minus xn and then capital K plus xn capital K minus L. Right, and so comes the triangle inequality. I can bound this here by moving the absolute value into the two differences. So I have xn minus xn capital K plus absolute value of xn capital K minus L. And I have control over both of them because give me anything that comes later than n. Okay, so here's a point that comes later than n. So then I'm squeezed in between epsilon over 2, squeezed in, then xn, the difference to xn to anything is going to be less than epsilon over 2. So that was this one. And then the same thing here, that I'll use the second part. And then I get that this is less than epsilon. This is the proof that Cauchy sequences are convergent. And so we should just reiterate that example we had from the beginning, the first example. So our square root 2 sequence, what was it? It was xn plus 1, which was a half xn plus 2 divided by xn. Our square root 2 sequence, this guy, shows that that q valued, like, so if I have, shows that if I take a sequence inside q that is Cauchy, shows that they exist such sequences that are Cauchy but don't converge in Q. So it shows that there exist such sequences that is Cauchy, but you do not converge in Q. And so the fancy word for this is, so the terminology that people use, is that Q is not complete. Q is not complete. And this is, there are limit points. There are limits of Cauchy sequences outside Q. And so for R is complete. All Cauchy sequences deconverge. All Cauchy sequences deconverge. So you can see the problem is that there are limiting, the Cauchy sequences that converge and they get to be outside Q. So what we're interested in is, so in words, you want to add, you add these limits from Q Cauchy sequences to Q to get Q's completion. Complete. T is E. So you add these limit points to get Q's completion, and this is voila. This is going to be R. We're not proving this last statement that we have down here, namely that if you take all possible Cauchy sequences of sequences in Q and you look at their limiting points, you take all those limits and you add them together with Q, then what you're going to get is exactly R. But this is one way to create the real numbers. It is by looking at all Cauchy sequences in Q, looking at their limit points and adding them to Q, and then this new larger set, that's going to be your set R. Are there any questions on what we have here? This is why Cauchy sequences are absolutely crucial. This notion of completeness, this comes up in many different. It's not just for the distinction between Q and R that one cares about completeness. You would care about this in lots of spaces that go beyond Q and R. And it's always the same. You're going to be looking at a notion of, you're going to have a sequence of sorts, and then you're going to be looking at Cauchy sequences, and then you want to know whether or not all Cauchy sequences are convergent or not. And for Q, the answer is no, but then you look at something that is bigger, that has the property, and then that bigger thing that has the property, well, in Q's case, it's going to be R. And this is indeed one way to define R. Are there any questions on this? One of you came to my office hours the other day, yesterday, I think it was, and asked if maybe we could do some more exercises. And so instead of taking you through more theory, I decided to solve a couple of problems from the textbook. And just, we have 25 minutes left and I have a couple of problems solved. I figured maybe we could go through, some problems. Are there any questions before you start doing that about the theory that we've been through? Right. So the first one I found that I think is useful to know is over here in the exercise 279. There's something called the ratio test. And so it's about a series where you have a sequence AN, and you want to know when the thing converges absolutely, right? So whenever you see the word absolutely, what that means is that you take absolute value of your A's in here. And remember, as soon as you're summing up something that is positive, after you take absolute values, say, then you get monotonicity, and you will always have a limit. The only potential problem is that it could explode. So you could sum up positive elements that would converge off to plus infinity, like this sequence 1 over n that we talked about so many times. So here is a condition. It says that if the ratio of these guys is not too big, then the thing converges absolutely. Okay, so let's see if we can get that thing to work. That was exercise 279. So what we have is you're taking a sequence inside R, and we're going to say that they're not 0. That's because we're going to be dividing, so we don't want it to be 0. Right, and what we're interested in, we want to know that we want to know what. So the assumption is, say that if I take the absolute value of these guys, and I take the limit, these ratios deconverge, and they converge to a number which is strictly less than 1. Say that this is true, then the claim is that the series of the absolute values, when I take the limit, this is finite. Right, there's no question about existence of a limit, right? This is a monotone. This is a monotone sequence. Right. The sequence I'm talking about is this one. This is a monotone sequence, so it has a limit. It has a limit in the extended real numbers, potentially equal to plus infinity. But what we're trying to prove here is that if the top part holds, then it does not explode. But I am free to write a limit here because it has monotone structure. And so how will one go about doing this? Well, it goes back to your homework. This is really a homework. The homework question about this summation of c to the nth. I forget what it was. Was it from 1 or was it from 0? I think it was from 1 you had it, and then it was c divided by 1 minus c. Does that seem familiar to you guys? Right, this here is for c somewhere in 0 to 1. So these things here, it might not seem like that homework question you guys just did has anything to do with this one up here, but it does. It really does. So how do we go about it? How do we go about it? Well, this is going to be equal to L, right? So if I pick some R prime, which is going to be between R and 1, such that I can find something in there such that AN plus 1 is less than R prime. Maybe I should call it C here, maybe to make it consistent with your homework. So I'll pick something like that. Right, this ratio converges to R. Okay, so if I just consider something that is potentially a little bit bigger, then I'll get an upper bound like that. And then I can iterate. I can iterate and say that the absolute value of an plus 2, well, that's going to be less than then c absolute value of an plus 1. And this is true for any n bigger than some big number. Right, and then I can do the same thing. I'll get c squared here, and then I'll have an here. And you can see now this is where the square comes in, and you can, this is what you guys were practicing on in the homework. We can iterate this up so that more generally I'll have that an plus m. Right, what would that be? This would be less than c to the m times the absolute value of an. Then I'll stick it into the sum we go. Like that's after all what I'm trying to prove. I would then say the sum, say from capital N, that's the lower bound I have up here, of an. Like again, there's no problem in this limit because these are all positive. And I'll do a little substitution. I would substitute here maybe instead of starting it at n, I could start it at 0. And then I would have an plus n here. And then I'll use the bound. And I'll use the bound. Here, this will be the sum from n equals 0 to infinity of an. This will be c. What would be c something big in absolute value of an. This thing here doesn't have anything to do with little n, so you can go outside. And then I'll have this sum, which is what you did in the homework. You did in the homework, I think it was from, maybe I forget if it was on 0 or 1 here, but it doesn't really matter. You see something like 1 over 1 minus c. Right, and that's fine. So if the absolute value converges, this is going to be much harder, right? So in particular, I'll have that the limit without the absolute values. In particular, I have that this limit here exists. And it also, and it's denoted. This thing here exists, which we denote. And we'll just denote it with an infinity upstairs. Maybe a little example to make this a little bit more, tangible. An example would be something like, I need that ratio. The key thing is this ratio on here. So take an example of an. This could be n divided by e to the n. Then I need to test, right? So I take an plus 1 divided by an. The ratio test would then require that I take n plus 1 divided by e to the n plus 1, that's upstairs, divided by what's downstairs, this is e to the n divided by e to the n, and then we take a limit. Take a limit. Where does it go? Well, where does it go? It goes to n plus 1 divided by n divided by, what would be downstairs, e to the 1. Again, the top part here, this converges to 1. This thing here converges to 1 divided by e to the 1. Again, this is strictly less than 1. So if I sum up these positive numbers from 0 to infinity, e to the so it'll be n times e to the minus n. This is this was the ratio test. Any questions about the ratio test? Actually, that was an example. There are lots of these in the textbook. I picked this one because I've seen it being used. I've used it myself. There are lots of other ones that I could have chosen. I chose this one. The other one that I have prepared is it's a follow-up on one of the things that we did early on. It's this alternating series test. And some of you might remember a thing that we did way in the beginning, this example. Just recall this example, I can maybe recall it on Mathematica. One of the things that we had looked at in the very beginning, and we already talked about it today too. So let me just go over maybe that again. So we're interested in summing. And so the thing that we had talked about for a while is this example, right? That's the thing. It doesn't decay fast enough. It doesn't converge. It blows up to plus infinity. So then the thing that we had talked about was that maybe we can make it alternating. Okay, so if I make it alternating, I have minus 1 to the n. And then we get this minus log of 2. And how does one prove something like that? If I don't have the alternation up here, the sum diverges, right? So this is a bad guy, right? If I take absolute value, this thing goes to plus infinity. So it's one of these sequences that is it's not absolutely convergent. It's only conditionally convergent, right? So how does one prove that there is such a limit? And that's what I wanted to. That's this exercise 271 that I prepared for you guys to have a look at too, right? So recall that if I sum 1 over n, this is plus infinity. We did that, but if I alternate the minus 1 to the nth over n, and I take a limit, this thing is actually in R. So how would one prove that? And Mathematica told me that it was like log of 2 or minus log of 2. So this is this exercise 271 that outlines how one should do it. So this exercise 271, it says, what are the ingredients? Well, you will take an positive and b decreasing to 0. And the one we have here is like 1 over n, right? So for us, the example that we had up here, an is like 1 over n. This is positive, and it decreases down to 0 as n goes to infinity. Then the statement is, if you take one of these sequences, then this alternating sum up here, then these Sn, the partial sums from 1 to capital N of this alternation, you switch the signs on the an, so this thing converges. And okay, so how does one prove that? It's not terribly hard, but there are a few tricks in here. So there are many ways to prove it. I think in this exercise, he has like 3 different ways that he wants to prove it. I was fiddling around with it this morning to see what would be a nice, clean way of doing it. So here's what I came up with. Right? If I look at S2, so what is that going to be equal to? It's going to be equal to A1, and then it swaps the sign to minus A2. Right? And then this thing is decreasing, right? So this is positive. This is because ANs are decreasing. So if I looked at S4, I would have A1 minus A2 plus A3 minus A4, right? It's alternating. And this would, of course, be S2, right? Plus this difference over here, but again, is decreasing. So if I threw it away, I'm going to get that. And so that's one thing. So S2n is bigger than S2n minus 1. Okay, so that was one property we came up with. Another property that came, so you see you have monotonicity. I'm not talking about monotonicity of the original sequence because I have a 2 here. So there's a subsequence that has a monotonicity property. So then we almost have a limit, but not quite. And we also need it to be bounded, right? So if I look at S2n, how would I write all that out? Well, I could write this out as A1 minus A2 plus A3 minus A4 plus A5 minus, and then keep going. And then I can put in parentheses, I can put in here A1 minus, and then what I'll have here is A2 minus A3 minus A4 minus A5 minus, and so on. And again, because I have monotonicity, this is positive. Again, this is positive. So there's a minus sign. So all of this, if I throw all these terms away, I'm just going to get something that is bigger. So I do have boundedness. So I have monotonicity, I have boundedness, voila, Bolzano-Weierstrass kicks in, and I have monotonicity and I have boundedness. I know I have a finite limit. This sequence converges. So boundedness and monotonicity, I know now that the limit as n goes to infinity of S2n, this exists and it's equal to L, this exists in R. Because it's monotone and it's bounded. Okay, but this is not quite what I had in mind. I would like to prove that not a subsequence converges, but I almost have it here. I almost have it here because we also have, this is where I'm using that it's alternating. It has a very nice structure. We also have that if I looked at S2 n plus 1, well then I would write this here as S2n plus, and then that limit, that extra element would be an plus 1. Right, and this here has a limit, and this one here has a limit 0. So therefore the limit of the left exists. Right, this here would be L. Right, because this thing here converges to 0. This was one of the assumptions that we had. The ANs converge to 0. So I now have this property that, so both S2n and S2n plus 1, they converge to L. Now we're gonna, so this, then the claim is that Sn also converges to L. And the proof of this claim is not too difficult. Like you pick an epsilon, and then for any n bigger than, say, n1, you can squeeze that guy together with L. You can squeeze him less than an epsilon. Again, for any n bigger than n2, you can squeeze the other guy less than epsilon with L. And so we need to prove that the original sequence converges. So for any n bigger than or equal to, so we always take a max here. So for any n bigger than the max of, say, 2n1 and 2n2 plus 1, what do we have? Well, we'll have that, maybe we should call this for m. We'll have that am, well, there are not that many options for it. Either it is going to be, either this is going to be odd or even. Right, so if it's even, it'll be equal to a2n for some n bigger than n1, or am is going to be equal to a2n plus 1 for some n bigger than n2. But regardless of I switched it around now. This should not be switched around. Shouldn't be A's. It should be S's. It should be S's. The only play I'm doing here is when I'm taking a natural number, that natural number is either going to be odd or even. Right, that is, m here is either going to be odd or even. If it is an even number, it's going to be equal to 2 times n. If it's going to be an odd number, it's going to be equal to 2n plus 1. Right? And then you just use the properties up here. Then you'll use the properties up here. You're going to be less than epsilon. So you can see this last part of the argument. It does not involve. This part here is general. It goes beyond just a particular example we have where the S's are given in terms of the A's. If you have such a structure here that these two particular subsequences deconverge, well, then the original sequence is going to converge. Okay. You guys have been very quiet today. Are there any questions or comments before we call it quits? It's the last part we will be doing on these sequences and series in chapter 2, and we'll move on to a different topic. We'll move on to these neighborhoods and balls and talk about topology on Wednesday. Could I have added them? Yeah, I could have done that too. I could have added them. Like there are many ways that you can express the original. There are many ways that you can express Sn in terms of these two here. And it's just a play on the fact that if here I have all the even and here I have all the odds. Right? So if I can control both the odds and the evens, then I can control everything. So I think you can also add them here. I think you can get that to work. Anything else? All right. Then I will see you guys on campus on Wednesday.